Okay, this is Chapter 11, Section 1. We're going to look at gases and pressure of gases. This section is quite wordy. You are going to need a calculator. We're going to do some real basic math on conversions today. But I will try to at least underline for you the important parts of what you need to know for some of these. So, for instance, pressure. Write down the definition for pressure. It is defined as the force per unit area on a surface. And some other important information going on here. It says gas pressure is caused by collisions of gas molecules with each other and with surfaces which they come into contact. So gas pressure is caused by collisions. And then the pressure exerted by gas does depend on volume, temperature, and number of molecules present. Volume, temperature, and the number of molecules present. The greater the number of collisions, the higher the pressure will be. So, greater the collisions, higher the pressure. So those two are going to be directly related. If we were to look at an equation that goes with this, pressure is equal to force divided by area. Pressure is equal to force divided by area. And this right here, if we were to look at the video is just going to show you adding air to the tire. The more air you add to the tire, the more molecules you have, and they will move faster because the pressure is greater. Okay, pressure and force. The SI unit for force is the Newton. So just making sure that you are familiar with some of these. So the unit for force is the Newton. We use a capital N to show it. And it gives you an example. Consider a person with a mass of 51 kilograms. At Earth's surface, the gravity is 9.8, so roughly 10 meters per second squared. So the force exerted would be approximately 500 kilograms times meter per second squared, or 500 newtons. So that very last part is trying to show you that the Newton, as far as units are concerned, is the same as this set of units. Kilogram, which is for mass, times meter per second squared. Meter per second squared are the units for acceleration. So that is meters for a distance, second squared, that's time squared. So kilogram times meter per second squared, the same thing as the Newton, which we use for force. And they're showing you another one worked out here. Again, the equation that we were talking about, pressure equals force over area. These bottom two bullet points are what I wanted to focus on. The greater the force on a given area, the greater the pressure. And the smaller the area for a given force, the greater the pressure. So in relations to this, if force increases, pressure increases. If area decreases, then pressure increases. So if we look at direct and inverse relationships, force and pressure are directly related. Area and pressure are inversely related. Another example that they're going to give showing this, and you don't have to draw this out, just make sure you understand it. They're showing a ballet dancer. If you look at her feet on the ground in the first example, you can see both feet are flat there on the ground, so a much larger area for her 500 newtons, so that is her weight. The force that she's exerting based on her mass, but then she gets up on her toes, the area is reduced, and now she's just on one foot with those set of toes. The area is reduced even further, but you can see the pressure exerted increases in each of those examples. Now, you've been introduced to pressure, force, and area. We're going to look at two different devices used to measure pressure. The first one that we're going to look at, and these will be separated here just a little bit, but the first one is called a barometer. And a barometer measures atmospheric pressure. So a barometer measures atmospheric pressure. Torricelli was someone that noticed about water pumps. They could raise water only to a maximum height of about 34 feet. He wondered why that was so and thought that the height must depend somehow on the weight of the water compared to the weight of the air. Because that 34 feet, as far as barometers go, and we'll look at a picture of a barometer here in just a second, correlates to, well, what if you were dealing with mercury? Because mercury rose to a height of about 30 inches or 760 millimeters. That's about 1/14 of that 34-foot height that we just looked at. So it is going to depend on the substance that you have, but there is a correlation there. So let's go look to see what a barometer looks like, and you should do a quick drawing of this in your notes too. So here is an example of Torricelli's barometer. Again, do a quick drawing here. You basically have a dish of mercury. So the dish of mercury, you have an inverted column with mercury in it, but atmospheric pressure is pushing down on that dish. And whatever pressure that is, and 1 atmosphere is considered to be atmospheric pressure, the barometer, the mercury inside of our tube, raises 760 millimeters, and then there's a vacuum at the end of that tube. So that is the pressure that, if you're doing atmospheric pressure, 1 atmosphere is basically equal to 760 millimeters of mercury, and we'll get to those correlations here pretty soon. But again, it does measure atmospheric pressure. We're going to add a couple more onto this just so that you have some conversion correlations. So again, I'm looking at this one right here, which is the one that I wrote down. 1 atmosphere is equal to 760 millimeters of mercury. So that's one pressure conversion. And 1 millimeter of mercury is equal to 1 torr. Again, that's named after the guy that came up with after Torricelli, that was looking at this particular experiment. We are going to look at some others on one of our next slides, and we're going to add to this and look at, well, 1 atmosphere is also equal to 101.325 kilopascals. So you've got to be introduced to, well, what is a pascal? And then if you look at your conversion sheet that I had given you in class earlier, the pink sheet, if you were here, some of these were already on that pink sheet. So the SI unit for pressure, is the Pascal or Pascal. It depends on who's saying what it is, but that is our unit. The Pascal is the force of 1 Newton acting on an area of 1 square meter. So 1 Newton per meter squared is equal to the Pascal. I wanted to write that out for you too, just exactly what I said. So Pascal is 1 Newton per meter squared. So force, Pascal is pressure, newtons is the unit for force, meter squared is the unit for area. So you have seen this already. And there was the other one that I had added to your list of units. Again, this set that I have the pink box around, these are the pressure conversions we're looking at as far as what 1 atmosphere is equal to. These are on your pink sheet, or you should at least have them in your notes. And we're going to go right now and do some conversions. I want you to set up your grid in your notes, and anytime you have any homework that goes with it, make sure you show your work. So for the first one, the average atmospheric pressure in Denver, Colorado is 0.83 atmospheres. Express this pressure in millimeters of mercury and kilopascals. So let's take the very first one. Whoops. 0.83 millimeters of mercury. Nope, sorry, that was atmospheres given. Atmospheres, and these are all one-step conversions that we have right now. Atmospheres can be converted directly to millimeters of mercury based on the graph we just looked at as far as what's equal to what. The number with atmospheres was 1, and the number with millimeters of mercury was 760, because 1 atmosphere does equal 760 millimeters of mercury. So when you work that out, you get 631 millimeters of mercury. Again, I would like to see all of your work. They also want this converted to kilopascals. And we did have a direct conversion between atmospheres and kilopascals on the previous slide. 1 atmosphere does equal 101.325 kilopascals. When you do your math, multiply everything on top, divide by what's on bottom, you get 84.1 kPa, or kilopascals. So moving on just a little bit, we are getting to Dalton's Law of partial pressures. So the pressure of each gas in a mixture is called the partial pressure of that gas. Now again, I'll try to highlight the important parts. Pressure of each gas in a mixture is the partial pressure of that gas. Each gas in a mixture is independent of the other gases. And then this definition for Dalton's Law of partial pressures: the total pressure of a gas mixture is the sum of the partial pressure of the component gases. And if we were to put this in equation form, it would look like this. The total pressure, P sub T, is equal to the partial pressure of each gas that you have. It just depends on how many you have. So dot, dot, dot. That is the sum of the pressure of the individual gases. So right now in that one, again, it's generic. I'm showing 3 gases that make up a mixture. Maybe you only have 2 gases. Maybe you have 5 gases. But you just continue to add partial pressures for each one. Now, we've looked at a barometer, which measures atmospheric pressure. Now let's go look at a U-tube manometer that measures contained gas pressure. So please do a quick drawing of this, and we're looking at, it's called a U-tube manometer. And manometers, unlike barometers, measure contained gas pressure. Measure contained gas pressure. So let's say you have a gas grill at home and you want to know what the pressure is inside of that gas propane tank that's in your gas grill. You could use a U-tube manometer. This one right here, we have a valve that you can open or close that is attached to a flask that contains a gas. And in this U-tube manometer, again, you got a valve right here, your U-tube that is right in through here. You would start off with a mercury level that is even on both sides. Even on both sides. So that way, whenever you open up that valve and let the gas come in through here, as that gas pushes down on the mercury on the other side will rise, and that difference in height that you have is going to translate to what the pressure is on the gas. So this is a U-tube manometer. So introducing you to another definition there at the bottom, talking about vapor pressure. You should write all of this down. The water molecules at the liquid surface will evaporate and mix with the gas molecules above it. The water vapor, like other gases, exerts a pressure known as vapor pressure. So again, they are outlining what vapor pressure actually is. So we have us another equation here. Your atmospheric pressure is equal to the pressure of the gas plus the pressure of the water. So you're looking at your vapor pressure of water. If you raise the bottle until the water levels inside and outside the bottle are the same, the total pressure outside and inside the bottle will also be the same. So again, we're going to look at a picture that goes with this on the next slide. But this is another side part of Dalton's Law of partial pressures. Again, atmospheric pressure is equal to the pressure of your gas plus the partial pressure of water. So in this picture right here, we have gas that is being formed. Just looking at colors here. Gas being formed in here. Acid and zinc are mixed together. A gas is formed. It's going to come down the tubing. The gas is going to come up and then into the bottom of this glass jar that is inverted. That glass jar that's inverted is filled with water. But as the gas rises, it will push the water out and the gas will be collected there in the top of the bottle. And that gas collected in the top of the bottle will have its own partial pressure. If I were to look at, again, the reaction that's going on here, we've got zinc plus sulfuric acid, bringing back some of your Chem 1 time, yields zinc sulfate plus hydrogen gas, and that is the gas that's being collected here. Let's go work out a sample problem. I would write this down and any work associated with it. Oxygen gas from the decomposition of potassium chlorate was collected by water displacement, so that's just like what we were looking at. The barometric pressure and the temperature during the experiment was 731 torr and 20 degrees Celsius. What was the partial pressure of the oxygen collected? So if I look at the equation that were to go with this, we've got the decomposition of potassium chlorate. It decomposes into potassium chloride and oxygen gas. Potassium chloride and oxygen gas. Now, at this point, so that we can finish our calculations we need to do, I am going to have a chart that's available for you on Google Classroom. If you're in class, I will also give you a copy of this, but you are going to need this table to work out your problems. It is Appendix B8. That one is listed wrong in here, but it is Appendix B8, which is on reference page R79. Again, a copy will be given to those in class or it'll be put online, and you will need that to work through this. So there's the equation that we are starting with. Atmospheric pressure is the pressure of the gas. The gas we're looking at is oxygen plus the partial pressure of water. Again, that's the water vapor that'll be collected on top. Have that table handy as we go through and put in some values. Pressure, and by the way, this is the equation that we're starting with, but it wants us to solve for the partial pressure of oxygen. If I were to rearrange this equation, partial pressure of oxygen would be equal to atmospheric pressure minus the pressure exerted by the water. So this is what we're solving for, partial pressure of oxygen. The pressure of, or atmospheric pressure, it tells us in the problem, is 731 torr. And we need to go find the pressure of water. I'm going to show y'all a picture of what that table looks like. Sorry, this is the picture we're working with. The writing's bled through on this, but just so that you can see what it looks like. And since we are looking for, going back to my problem, looking at it, it looks like a pressure at 20 degrees Celsius for the pressure of water. At 20 degrees Celsius, the partial pressure of water is 17.5 millimeters of mercury, or 2.34 kilopascals. If you recall, the torr and millimeters of mercury are 1 to 1. So if that's 17.5 millimeters of mercury, that's also 17.5 torr. So heading on back over here, from that chart, we have 17.5 millimeters of mercury, 17.5 torr for the partial pressure of water at 20 degrees Celsius. And when we subtract that, our partial pressure of oxygen ends up being 713.5 torr, or 713.5 millimeters of mercury. So again, make sure you show these worked out within your homework.